In today's video, what we're going to do is we're going to talk about some basic fluid flow calculations that you'll be doing for practice and for your assignment. Now, this is the PowerPoint that you guys have already been supplied. What we're going to do is we're going to skip down to slide 4. Slide 4 talks about the 3 different types of flow. We can have a laminar flow, we can have a turbulent flow, or we can have a transitional flow. The way that we actually figure out what type of flow we have is we're going to use something called the Reynolds number. The Reynolds number does not have a unit, it's just basically a number, and we can use that value to determine whether it's laminar or turbulent. Now, for when we do calculations with piping, if we have a Reynolds number that's below 2100, it is laminar. If the Reynolds number is above 4000, it's going to be turbulent. If it's between those two numbers, it's going to be transitional. For other flows, and you can see the calculation is a little bit different than the pipe calculation, we're going to be given a particular number. So we'll be giving the number that's going to help us determine whether it's laminar, turbulent, or transitional. So these numbers only apply for pipes. So for the other flows, we'll probably have some sort of a length that might say over this much space, it'll be laminar, and then it'll transition to turbulent. So we have to look at the problem to see what we're doing for those particular types of calculations. Okay, now we're going to skip down to another slide 8 to talk about boundary layers. This is the other type of calculation that you'll be doing with fluid flow. So we have some sort of a fluid that's getting ready to flow over an object. You can see that this flow is moving towards the object. Now it'll hit the object and then it'll basically go around it. The friction is probably going to be very high where the fluid is basically flowing along the object, so it's going to slow it down. And as you get further and further away from the object, the speed will be going back to its original speed. Okay? So the boundary layer thickness is basically determined wherever that fluid flow velocity is basically 99% of its original flow. Okay, so that boundary layer is something that can be calculated. You may be used to seeing that if you're looking overhead of a boat, you can actually see the boat traveling and you see the ripples that go around it. That's the easiest way to explain it. Behind the object, there's a pretty stationary or stagnant area, and that's called the wake. So that is probably an ideal place to be when you're doing flow. That way you don't encompass any friction, you don't encompass too much velocity when you're trying to go through that particular type of fluid. Okay? Now, to calculate the boundary layer, it depends upon whether the flow is laminar or turbulent. So we've got 2 different equations here, okay? And the unit here is going to be either meters or feet, depending upon the unit that you have, or the system of measurement that you're working in. So for laminar flow, we're going to take 5 times the x dimension, and that's basically the distance along the plate or along the object. So let's say that we go 0.1 meters or we go 1 meter. That's what the x value would be, okay? So 5 times x over the square root of the Reynolds number. For a turbulent flow, it's going to be 0.37x, that number, divided by the 5th root of Reynolds number. Okay, so this equation is going to be different depending upon what type of flow you have. Okay, again, x is the horizontal dimension along the object. Okay, now what we're going to do is we're going to do an example together so you can see how these are calculated. And you can set up an Excel problem, set up a spreadsheet in Excel to do this calculation for you to make it a lot easier. So here we have if air is flowing over a flat plate is laminar for the first 0.3, so that's the transition, and then it becomes turbulent. What is the thickness of the boundary layer at the following points along the plate? The free stream velocity is 30 meters per second. So if we go back to this figure that we see, this velocity is 30 meters per second, and we're trying to figure out what this shape would actually be, okay? So going back to here, I've gone ahead and looked up the values for us for air, I've got the density, okay, and I've got this other value here, okay. I've already have a spreadsheet set up for you guys, so we can use this spreadsheet here to help us figure out what this problem is. So move that over a little bit for you. Okay, so I've got all my equations up here for a reference. For my density, I'm going to go ahead and put in the value that I looked up, and that's going to be 1.23. For my length, that's going to be the x dimension, so I'm just going to type that in. My velocity in my example is going to be 30 meters per second, so I'll type in 30. And my viscosity that I looked up is 1.79 times 10 to the negative fifth. Okay. All right, and you can see it simplifies it for me. Now my x coordinates that I need in my problem are in increments of 0.1 from 0.1 to 0.6. So I'm going to go 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6. So my problem is set up. I'm going to go ahead and do my calculation for Reynolds number, and I really only have to put this equation in once because I can copy and paste it for the other rows. So I'm going to go equals, and you can see my equations up here. I'm going to go ahead and select my density. Now the thing is that when I copy and paste this formula, it'll look to move down also. So I want to make sure that I put an absolute reference here. And if you remember, the absolute reference, I need to put a $sign in front of the letter and the number, okay? So I've got that, I've got my density, and then I'm going to multiply my length, okay? And then I'm going to multiply my velocity. I also need to put an absolute reference there as well, okay? So there's my absolute reference. That takes care of my numerator. Now my denominator, it's basically the viscosity. So I'm going to divide that by the viscosity, and I also need to have an absolute reference in there. Okay? Now I've gone ahead and calculated that out, and there's really no need to redo that. I can just copy and paste that all the way down. Okay? There we go. We're set for right now. The next thing I want to do is I want to go ahead and fill in my values here. Now this is going to be L/T. I went ahead and put a column in there to say, is it laminar or is it turbulent? So what I'm going to do, I can either type it in by hand, or if I wanted to, I could use logic in Excel. And I'm going to go ahead and do that. I'm going to go ahead and put in another row. And I'm going to say here, critical value, okay? And I'm going to go ahead and type in 0.3 here. That way I know anything below 0.3 is laminar. Anything that is above it is going to be turbulent. So I'm going to go ahead and use logic, and this is a good review for logic. So with logic, I'm going to use the if command. I'm going to go equals if, okay? And what I'm going to do is I'm going to test to see if this value is greater than this value, but I want to go ahead and put an absolute reference for the C10. That way I only have to build this equation once, and I can just copy and paste it all the way down. Okay, and if you look at my little helper right here, I'll put a comma, and now it's going to tell me what I should put if it's true. So if this value is greater than the 0.3, then I'm going to display turbulent. And I have to put it in quotes because it's text. And now the other case is going to be laminar. And then I close it out. So again, I got my equals if. I've got my test here, and I'm going to make sure I put an absolute reference that way I can copy and paste it all the way down. I'm going to display a turbulent if this value is bigger than the 0.3, and it's going to display a laminar if it's less than. And there we go. Okay? So that's really good. I'm going to go ahead and I'm going to copy this, and I'm going to paste it all the way down. So I only have to do it once, and you can see it does what it's supposed to. Now I'm going to go ahead and calculate my boundary layer thickness here using the logic that I just practiced again. So I'm going to say, I want to do that up at the top. That way it's easier to do. I'm going to say equals if And in this case, I'm going to use the same exact logic test. I'm going to click on this value. If it is greater than this value, and I'm going to go ahead and put my absolute reference in, that way I can copy and paste it. If it's greater, I'm going to do a calculation. Now I'm going to use these equations up here. So if it's greater, I'm going to do my turbulent calculation. So I'm going to go ahead and put in some parentheses here. Okay, 0.37 times my length divided by my Reynolds number except I choose the wrong value there. My Reynolds number raised to the 0.2 because that's the fifth root, okay? And I'm going to go ahead and put in the other equation here for my laminar calculation. 5 times the value divided by the Reynolds number to the 0.5. And I'll close it, close the overall calculation, and there we go. Okay? And I can just go ahead and copy this and paste it all the way down. There we are. And that's my values for my boundary layers. Okay? Now, once I have this, if I wanted to do a graph, I could graph this as the x coordinate and this is the y coordinate. I could get a very nice graph for my boundary layer. I can actually see what it looks like. Okay? But as far as doing the actual problem, that's really all that we need.